In this video, we're going to work a couple more examples where we can use our understanding of the inverse trig functions. Here we have an equation where we're asked to solve for x, and the value of x is located in the argument of an inverse trig function. In order to solve for this x, what we need to do is to isolate the inverse trig function, or isolate that which is holding that x variable captive. So we begin by dividing both sides of the equation by -6. So after the -6 cancel on the left-hand side, we end up with just sine inverse of 3x, and on the right-hand side we have -pi/6. So let's think about what this equation is now telling us. We can think about this equation in one of two ways. First of all, sine inverse of 3x is equal to -pi/6. This is describing the same relationship as is described by the regular sine function of the angle is equal to 3x. So we have two different ways of looking at this relationship. The inverse trig function is going to have an output that is an angle, and then regular trig function operates on that angle. So we're going to convert out of the inverse sine function and back to regular sine, because from here we can evaluate the sine of -pi/6. -pi/6 is down in the fourth quadrant, and the sine of -pi/6 is -1/2. So the value of the left-hand side of this equation turns out to be -1/2, so we can substitute -1/2 in for that entire side, and then the right-hand side of the equation stays the same, of course, as 3x. Now I have a cute little linear equation, and we can solve for x simply by dividing both sides by 3. So -1/2 divided by 3 is -1/6. So we'll want to, of course, check our answer, -1/6, by storing this value into x in our calculator. So we come over here to our calculator and we input -1/6. We use the store function and we store it into an accessible variable. X is a very easy one to store it into. So we've got this decimal value. Now we want to plug that value back into the original equation in order to see if it's right. Something that we will want to be sure of is that our calculator is in radian mode. Notice that we have the inverse sine of some value is equal to an angle, and that angle pi is given to us in radian mode. So let's get our calculator into radians so that our answer comes out clean. So we'll come out here and go into mode, and I'll need to change this over from degrees into radians, and then I'll be able to look at -6. I'm simply typing in the left-hand side of this equation, inverse sine of 3x, where x is taking on the value that I have stored into it, and hopefully this turns out to be the decimal value of pi, which is what we were expecting. So our answer, x is equal to -1/6, actually does work. Let's look at another example. We're asked to write the trig expression as an algebraic expression in terms of u, meaning we do not want to have any trigonometric functions in the expression. Well, this seems a little weird. So what we'll notice is that we actually get a little information by looking at this inverse sine function. We know a couple of things. Inverse sine of u is going to have an output that is an angle. So let's consider that angle for a moment. If inverse sine of u is equal to theta, well then that tells me, of course, that the sine of theta is equal to u, and I can graph this angle in one of the quadrants. Now, as you may recall, the inverse sine function is going to have an output possibility of either the first or the fourth quadrant. So whatever theta turns out to be, it's going to be in either the first or the fourth quadrant. Now, what we come up with as an algebraic expression is going to have to work whether or not the angle turns out in the first or the fourth. So for right now, let's choose an easy quadrant, the first quadrant, and then hope that what we come up with as a solution also works for the fourth. So let's just arbitrarily sketch our angle theta so that it's existing in the first quadrant. And all we know about this guy is that he has a sine that is u. So if I were to drop a perpendicular down to the x-axis, I know that the ratio between the opposite and the hypotenuse side reduces down to being u. So I can label up my right triangle saying, well, the opposite side would be u, the hypotenuse side could be 1, and this would be a triangle where the sine of theta is u. We can then use the Pythagorean theorem to figure out the length of the adjacent side. And we would want to write the length of that adjacent side in terms of u as well. The reason why we want to write all of our sides in terms of u is that if I have my entire triangle written in terms of u, then I can certainly evaluate the tangent and express that in terms of u as well, which is what we were asked to do, to write the trig expression in terms of u. So I need to get the adjacent side in terms of u. So in this equation, we just subtract u squared from both sides and then take the square root of both sides to get the length of that side is going to be 1 minus u squared under the radical. Now, generally speaking, when I take the square root of both sides, I consider the plus or minus. However, if I'm in the first quadrant or in the fourth quadrant, which is what theta has the option to be, in both cases, the adjacent side of this triangle is going to carry a positive value because it corresponds to the x-coordinate, which is positive in the first or the fourth quadrant. So we really only have to express this in terms of the positive radical. So now we have our triangle as it is drawn in the first quadrant, where all the legs of the triangle and the hypotenuse side are all written in terms of u, or our constants. And since I have my triangle that's complete, I can now determine the tangent of that angle theta. Remember, our original equation, or the original expression, was tell me who the tangent of the inverse sine of u is. Well, inverse sine of u has an output that is the angle. So this is saying the same thing. Tell me who the tangent of that angle is. And we want the tangent of that angle to be expressed in terms of u. And so as we know, tangent is equal to the opposite over the adjacent side. So the tangent of theta is going to be my opposite side over my adjacent side, which is 1 minus u squared. Again, this is assuming that the angle was in the first quadrant. So let's have a brief discussion of what would happen if the angle fell in the fourth quadrant. If sine inverse u was describing an angle theta that fell in the fourth quadrant, we would draw a reference triangle back to the x-axis. And on our reference triangle, we would label the sides such that the opposite side was u and the hypotenuse side was 1 again. By our Pythagorean theorem, we could solve for the adjacent side in a similar way, and we would get 1 minus this u squared underneath the radical again. Now, what's different here is that this vertical side is going to take on a negative quantity. The value of u is going to be negative if I end up with an angle that's in the fourth quadrant. If u is negative, then the sine of that angle theta is a negative quantity, which is what we would expect for an angle that falls in the fourth quadrant anyways. But also, if that angle is in the fourth quadrant, the tangent of that angle should turn out to be a negative quantity as well. Well, what did we determine was the value of our tangent? We came up with the formula that the tangent of that angle was u over the square root of 1 minus u squared. Well, if theta is in the quadrant 4, then the tangent should be negative. And our equation that we have established for tangent has the value of u in the numerator of our fraction, which is a negative quantity in the fourth quadrant. So this formula that we've come up with for the tangent of that theta allows for it to be positive if theta is in the first quadrant, because u would be positive in the first quadrant, but it would also take on a negative value if theta were in the fourth quadrant, because if theta is in the fourth quadrant, our value of u is negative, and the formula that we've come up with for the tangent turns out to be negative. So this formula works no matter where our angle theta falls, in the first quadrant or in the fourth quadrant. And based on our original problem, those are the only two possibilities for our angle theta, because of the fact that we were looking at the inverse sine as our inside function.